Thank you, Irfan. So can you please confirm that you can see my slides?
Yes, we can see them.
All right, that's perfect. All right, thank you very much. I'm very pleased to be able to share some of our recent development in the control software and firmware. My name is Anastasiia Butko, and I am a research scientist at the Lawrence Berkeley National Lab. So I would like to first give you a little bit of the outline that I'm going to follow during my talk. It's going to consist of three main topics. First, I will introduce a little bit about our user experience that we would like to provide. And I would like to talk about the control stack in terms of the abstraction levels. And at the end, I will going to go deeper into the system architecture and how we evaluate and also implement it for the quantum testbed. So in terms of the user experience, something that we would like to emphasize is that quantum control system is what will define user experience, because it will define it in a way that providing some features by having such modularity, performance, scalability, and transparency. So it is easy to adopt and use, and it's going to dictate the experimental protocol for the continuing quantum research. So our goal is to develop and explore a quantum control system such as to enable as much functionalities as required by the experiments, to provide scalable and modular support for quantum chips with the increasing sizes in the future. Also to be open and transparent, as I said, for the community to be able to modify it and adapt as we develop the quantum infrastructure. And for sure, we would like to make sure that we keep in mind the big picture of how those quantum accelerators and chips will be integrated into a big system like super facility case. So with this being said, I will be explaining the control stack in terms of the abstraction levels, but also focusing particularly on the awareness across the control stack, because the awareness across the stack will define the trade-off between the flexibility and the modularity of the system. So in the high-level abstraction levels, we see in general quantum computational model as well as quantum algorithms. So those two levels, general levels for sure, they have been an active area of research for a very long time, way before any physical implementation of the quantum computer became available. And even those the recent development for the NISC applications bring the awareness about the hardware up to the levels of software, it's still important to keep it more hardware agnostic to be able to provide a certain level of modularity. So on the low level, we have hardware and some very low level control that operate at the level of physical pulses and have very little or no notion about the software that is being run on top of that. And then on the middle of those two levels, we have the levels that are both hardware and software aware, that are bridging the gap in between the theory and the practice. So those levels in general include quantum gate sets, quantum circuits, as well as the control unit that the main functionality is to control and manage the data flow, manage timing, pulse, having the ability to pulse, to shape the pulses, and also store those pulses in some sort of the library. So in the next few slides, I'm gonna talk more about the control unit and two general approaches on how this control unit can be implemented. So I will talk about the control unit in terms of the system architecture to explain about the proximity and the functionality of this unit. So this is a little bit different diagram of the same approach that I would like you to focus on two sides. On the left, we have the user host computer that runs the software. It can include algorithms and compilers and circuits. And then at the end, we have a sequence of pulses. And then on the right, we have some sort of the classical control and all of the control and data management is happening in the hot PC, and at the end you just load your program that is precompiled on the classical control, and then you let it run without having further control on the top of that. So this is a software approach, and it does have its benefits as well as disadvantages. So among the benefits, I would like to list the fact that in this case, we have everything in one place. And I mean everything in terms of the software control. It is easier to implement and modify, and it is very suitable for the NISQ experiments. So from the disadvantages, I would like to focus your attention on the fact that you have to deal with the latency in between the host control and the classical control, as well as be aware about the limited bandwidths in between those two in terms of the limited flexibility, because as soon as you load your control sequence, there is very little you can do about the experiment itself. And that will lead to a limited or poor scalability in the future. So the second approach is to replace this load with a quantum control processor in a closer proximity to the low-level control hardware. That would allow us to reduce the latency, provide fast feedback, provide extended functionality in place. It can potentially improve the scalability. It allows us to separate the concepts, and it will be more suitable for the experiments beyond NISQ. Among the disadvantages of this approach, I would like to emphasize those two, which are the fact that it might require some specialized solution, and it will be extremely important in the case if in the future the close proximity will mean actually be in the fridge, for example. And in this case, we will need to provide special solutions because you cannot implement a regular microprocessor with the regular microarchitecture using new technologies like superconducting electronics inside the fridge because of the specifics of this technology. And the second bullet is it is harder to implement and modify compared to the software functionalities. So with those two disadvantages in mind, we would like to address those challenges in two different ways. So the first challenge we address by exploring the quantum instruction set architecture that would allow us to support quantum operations, timing control, and some other functionality in a more explicit and special way compared to general purpose processors. It would allow us to be transparent, adaptable, and open. And in our current implementation, we implement quantum instruction set as an extension to a commonly used RISC-V ISA, which is open and modular. It has a very active community, and it already has a very sophisticated ecosystem. I will talk a little bit about the QUASAR later, but in terms of the second challenge, which is harder to implement and modify, we would like to use new tools in hardware design and evaluation. And over the past decade, there were a lot of development on how to facilitate and simplify actually the exploration and the development of the hardware by using high-level hardware description languages, for example, like Chisel, that would allow those hardware modules to be parameterizable and easier to explore. So in terms of the quasar exploration, we did we did a very broad research by first designing a specific methodology that would allow us to better understand the capabilities and limitations of the existing processors, and also compare our proposed approach to alternative solutions that already exist. And combining those two, we have been able to provide some guidelines on what is the best way in which cases to design those quantum ISAs to provide the best encoding efficiency, the best performance, the best program size, for example, etc. So this research have been available as a publication, and they put a link to the archive. So be aware that the current version is not the most recent one, and the new version is going to be uploaded, or it will be available since it's been uploaded, will be available within the next week. That is more extended compared to the first version. So moving forward to this to the last subsection, which is the system architecture implementation. So we have been able to integrate all of those pieces together in a single system using Freedom platform for system integration on an VC707 FPGA. So this system, as you see on the slide, has three components. It has a RISC-V regular core that run Linux, manages remote communications, do some periphery support, and provide some extra security layers. It does have the Quasar extension implemented as a coprocessor, and that it do manage all of the upper mentioned functionalities. And the third component is Cubic, that you have already heard this morning from QUASAR's talk, which is an analog backend that manages phase manipulations. It does fast readout, timing control, some other functionalities. So this system has been implemented, but also we provide some support in terms of the software, in terms of the Quasar library that would allow us to connect to higher level software tools, Qtrl, that QUASAR has been talking about, also OpenQASM, and do some translation in between those tools, and provide the best user experience that to continue the quantum research. So I would like to thank you. This is a short summary of my talk today. I was talking about the user experience and how it is defined by the functionality and capabilities of the control stack. I was walking through the control stack in terms of the awareness across the abstraction levels, and I talked about our system architecture and some of the development that have already been made for the quantum testbed. So I'd like to thank you again, and here is the list of the team who participate in this particular research. Thank you very much.